Okay, there we go. Whoa. Okay, so my name is Amy Glass. I am Information Services Librarian at Illinois Central College at the East Peoria campus. And welcome today to Think Like a Scientist 2.0, a panel discussion. And this is tied to our One Book, One College presentation. And our title for this year, Think Again by Adam Grant. It's a really great book. If you haven't had a chance to pick it up and read it, I would strongly suggest that. We have three panelists here from Illinois Central College here, and they actually did set themselves in alphabetical order here. So we have to my far left, maybe depending how you're watching, your far right, Kristin Jacobson Flex, who's a professor of biology here at ICC. Next to her is Brad Rose, who is assistant professor of chemistry. Is that correct? Or are you full professor at this point? He doesn't know.
Yeah, the second one, whatever.
Whatever. Okay.
Not full.
Okay, and then we have Vincent Strow, who is the program director of the Medical Laboratory Technician program here. So I have some questions here prepared for them. So my first question to you is, how do you define thinking like a scientist? And Kristin, if you'd like to start. Oh, she brought
I
notes.
did, I wrote notes. Yeah, my husband asked me last night, he's like, how do we think like scientists? And then he Googled it to check to see if I was right. I don't know that what I say is what everybody else would think. But what I was saying is that pretty much science is observation and then follow up on that. And so I think that everybody all the time is thinking like a scientist. If you observe something and then you come into a situation and you have to decide what to do with that information, that is scientific thinking. I think the people who do it the best are 2-year-olds and 3-year-olds and 4-year-olds, because the whole world is new to them. And they come into it and they pick things up, they taste them, right? Think of your son, right? He's thinking like a scientist entirely. And as we get older, we kind of stop sort of interacting with the world in that way. But that would be what I'd say. I'm looking for patterns and looking for ways that we can test our thought process.
Okay, Brad?
Yeah, so to add to that a little bit, I think to me the key point is revision of ideas and overcoming previous biases that you have. And like Kristin said, with a kid, it's easy because they have no strong bias or opinion to favor one thing previously. But the hard thing is to, when you have a strong opinion, being open to revising and revisiting that. So one framing I like to think about it in is for the mindset, either a scout mindset or a soldier mindset, where a soldier mindset is to, I'm defending this idea. This is my previous belief and bias. And sometimes that's okay to do. But sometimes you also want to be in the scout mindset, which is also an important part in like the army analogy, to go observe reality. Where is the other army so we can position things? It doesn't matter what bias you have. If you want them to be over here, where are they actually? And report back that factual information. So to me, that's the hallmark of it.
Vincent?
Well, they've both given really good explanations as to what it might be to think like a scientist. I would succinctly put it as asking yourself the question, if something happens, is it going to happen every time like that? And if the answer is, I don't know, well, then what do? You do it again. You hit the button, you do the thing, you knock something over, and you write down whether or not it happened again. And that, I think, is the simplest part of thinking like a scientist, is what has the evidence shown us? What is the repeatability of this whole process? Are we going to see the same result every time? And if the result changed or the outcome changed, what could cause that? What have we missed? What could influence that? You can apply that to just about anything in the world. Like, we've all gone into a classroom and sat down because we know if we go into a classroom and sat down, like, that's what's going to happen. We know that we're not going to sit down and then explode, like through trial and error. If you are 2 years old and you're going into a room, you don't know what's going to happen in the room until you've done it enough times, but you're probably going to go sit down even if there is a risk of explosion, because you don't yet know that that is a risk. Like that, I think is the simplest way to put it. And then, of course, as we get older and as other things happen, like it becomes harder and harder to do that.
Something funny that he just said, you brought up trial and error, but using trial and error to work through problems. I think that's another succinct way to do it. Is that is what the process is. You try something, did that work? Sure, then you do it again. If it didn't work, then you try something different. And people think, I just think that in general, the word science is a 4-letter word to most people, right? It is, we make it scary, and that's why I started with kids. Kids don't think it's scary. But as soon as we get to the point where it's a class, then people are like, oh, I can't do science. I'm like, you do science every day. Every time you're making the process, I thought you are doing science. So I think that's part of this.
Okay, now I'm gonna throw these guys a little bit here with a side question and a quote that I found. This is from Adam Grant, the guy who wrote Think Again. Kristen might have heard this already, but I'm not sure the other two have. This is his definition of thinking like a scientist. Thinking like a scientist does not mean you need to own a telescope or a microscope. It just means you favor humility over pride and curiosity over conviction. So I think that ties back into the 2 to 3-year-old thing that we mentioned. You know what you don't know, and you're eager to discover new things. You don't let your ideas become your identity. You look for reasons why you might be wrong, not just reasons why you might be right. You listen to ideas that make you think hard, not just the ones that make you feel good. And you surround yourself with people who can challenge your process, not just the ones who agree with your conclusion. Do you have any follow-up to say on that?
Well, it's interesting that you said science is kind of like a 4-letter word. And I've had many discussions where people are like, well, you know, big science, big pharma, all the influence, all the corruption. This is why science is bad, this is why I don't listen to it, etc. And I always kind of laugh at that because scientists know that their views, their publications, their research has to be able to stand up to scrutiny. And so the way I explain it is there's nothing more, maybe I'm a bit of a mean person, but there's nothing I enjoy more than being right. And the easiest way to be right is to think about how could you be wrong and then come up with answers or defense of that. And if other scientists are going and looking at your work, your research, your whatever you've done, they're going to be thinking like, how has this person messed up and how can I get published, figuring out what they did wrong and undoing the conclusion. Like that's that. Maybe I'm a very combative mindset, but that is one of the things I find be really helpful in developing confidence in the process of science and research, is that you have people out there who are going to challenge your findings, and you need to be confident enough that you can defend what you discovered, what you found, or what you put forward. Because your name's on it and you're trying to claim something, you should be able to back it up. If you can't back it up or you don't know why you can back it up, or you don't actually know what you're doing, then it's not good science.
I like the part about surrounding yourself with people with different views. I think that is not something we do great in our society, right? That's partially why we picked this book for one book in college, is we knew that this was the thing that we needed to deal with. But I do feel like that's how you're going to learn the most, is when you hear other people. And yeah, I that just speaks to me, and I think that it's good. I think that science doesn't always, in practice, as Brett was saying, I don't think it always works that way. Scientists do sometimes get pet hypotheses, and it's hard not to do that. You kind of have an idea. I'm sure this panel is a little different than the one in the fall, because we have been in the labs and such. It's hard to not pick an idea that seems logical and go with it. You have to kind of look at all of the different possibilities and not go in with preconceived notions. We're humans, and so it's hard for us to do that. But I like, that's what's good about having the other people sort of come in and question what you're doing.
Yeah, I would say we're humans, bias is just built into us,
Yeah.
it's baked in. It's not necessarily a bad thing, it's something to deal with. So like when Vincent said, for drug companies and all these panels at FDA are too big, you can't trust them. I think you can flip that around and say, okay, what's the alternative? if we want to provide medicines on a widely distributed level that work, maybe there's a better process. What could we do? But I don't know of any. It doesn't mean there isn't one, but it works well enough to where it's open to refinement. But there, of course, are biases. You're going to have people that are going to have their digging in areas that aren't necessarily warranted. And famous or maybe infamous example, this is Albert Einstein, when he's quoted as saying God does not play dice because he hated the implications of quantum mechanics, and that its root level reality has randomness to it, because that goes against his beliefs, prior beliefs, religions, things like that, of the clockwork universe, to where if I know everything now, I can predict it in 10 years perfectly. If there's that grain of randomness inherently at the root level, that goes out the window and has a lot of philosophical implications that he was famously wrong on for all the great things he did. So you can't just trust someone because, oh, they've done some other good things. Well, they can be incredibly wrong in certain areas if they just haven't been pushed enough or thought about it quite the right way as well.
Yeah. When we had our thing last fall, Aaron James was one of our philosophy professor on here, and he touched on a lot of that too.
Yeah.
So, and I know this is for the experts, but I had two things to add to that. You mentioned science is a 4-letter word. I would also add to that failure is also a 4-letter word. You know, that we're afraid to fail.
Yeah.
So that doesn't really, you know, we give up after a certain point with that. The other thing is that what I think it was something you've mentioned, Vincent, about the whole idea that the best way to know if you're right is to look at it from a different way or something. I don't know how you did that. And when I do library instruction, especially for English 111 classes where they have to do an argument paper, I say, you gotta, if you're gonna have facts to prove, you know, or something to say, this is what I believe, you better have an answer for somebody else who's gonna say, well, that's not what I believe, kind of thing. You have to think it from both points.
When I do discussion boards, I always tell them, you have to go and find somebody that has a differing view from you and comment at least on one of those differing views, because otherwise you can go find, oh yeah, that's great, right? You can go agree with 5 people who are the same, you know, you're not learning a whole lot in that way. So if you have to go and read what somebody says that's completely the opposite and listen to that in an academic setting, then you're gonna expand and maybe learn something from that. That is how we grow, so.
Our next question, how do you encourage your students in your classes to think like a scientist? For the science classes, this is probably a more obvious question in some ways, but maybe not. So, Vincent, would you like to go first on that one?
Sure. So I do clinical laboratory or medical laboratory technician program. So we do a lot of the practical cases. We talk about what happens in the real world, quote unquote, when you're doing procedures or trying to come to a conclusion about a patient or the testing results, et cetera. And one of my favorite things to do for the students is like give them the real world examples, because when you're a student, a lot of times we give you, I don't want to call it sterilized, but textbook examples, you know, where it's really kind of more clear cut than it might be. But as I'm fond of saying, there are 2 things I like to say. One is that pregnancy screws everything up. And 2 is that the real world is not so clear cut. You have everything in between a yes and a no. So you have to be able to factor that into what might be explaining these results, or what might be causing a false test result or interference of some kind. So I challenge them to provide me with what is the answer here, but then give me 2 other explanations as to why we have these results. And sometimes that could be answers like someone literally didn't do the test correctly, or it could be that there's a pre-analytical thing that completely throws off the testing entirely. So they have to think not just, well, what's the textbook answer for your exam where I'm not trying to trick you, but then in the real world, what do you have to think about? Like, what are you having to watch out for? Because again, your conclusion has to stand up, and in the real world, it's not as easy. So.
Brad?
Yeah, I would say with a lot of the content for chemistry anyways, connecting it to kind of give it meaning in their life helps. And another thing just in general with academics, not even science necessarily, is the beauty of it is I think we're basically trying on ideas, like trying on clothes. So I try on clothes, maybe I like it, maybe I don't. but it doesn't identify who I am. So same thing as we're going through these ideas, that if it pushes back against your belief or your previous biases, then trying it on, saying, well, what if I humor it? What if I did believe this? Why would I believe that, or what evidence is there for that? To further refine and make your thoughts and everything a little bit more robust. And I like to provide examples, the humility, like I love it when I'm wrong and I find out new things where my previous beliefs are incorrect. So a recent example was maybe a month ago, I was listening to a panel of specialist doctors talking about, to me, kind of a gold standard in the medical field is a double-blind study, shows if it works. But I had never thought about, well, if you have a disease that's not well understood and you have a couple different types of it, if you're testing a drug, maybe this drug works on the one type, but not the other type. And with the double-blind study, you can miss that. So it's not as robust in a gold standard necessarily. Even that has its own flaws that you need to think about and question those assumptions going into it to help refine and get a better outcome and say, oh, maybe there is this little subtype that it really did work on, but we missed in our double-blind study the way that we set it up and approached it. Which again, to me, that's awesome. I never thought about that. That changed my views on it entirely. And I find that really exciting and rewarding.
All of these are great. I do 3 different kinds of classes, and so I do it differently in different classes. So the students that are here in my conservation biology class, and in conservation, we have a lot of not black and white topics. We have a lot of stuff we're just moving into now that's, as you said, somewhere between here and here. A lot of times it seems logical. If we've got animals and we think it's the right thing to save these animals, why don't we just do it? Well, there's usually so many, like with the lab, so many confounding reasons, land or money or the viability of that animal. And so trying to get them to think about all the different variables that could impact those in that class. And in 114, we have them actually role play and do kind of and give them a role that's not them. Like, so if I know I've got a student who's a hunter, I make them a tree hugger. And if I know I have somebody who comes in and they're, dressed to the hilt, like me, like a hippie, then I'm going to make them one of the people that's going to have to be a hunter or support that. And then they have to play that role. And boy, is that uncomfortable. You can see literally squirming. But by the end, the goal of that one activity is to come up with a plan for hunting wolves in Michigan, or if they should be hunting wolves. And we always come to some sort of conclusion. Depending on who the strongest students are, it's a different conclusion every time, but that's a really fun way to do it. And then I do field biology. In field biology, I don't do a whole lot. I make them 2-year-olds again. I send them out into the wild and I'm like, go discover. And so much of science is observation, so much of it. And so they learn a lot and they start to make connections. And then they come to me and they're like, oh, remember when we were there? And this was like that. And there's no teaching involved. They teach themselves. And so I think that that's a lot of what we could do is get out of the way and kind of let them unlearn what we've taught them, which is sitting down and shutting up the desired behavior. As you said, that they all know now. Yeah.
What do you see as a drawback of thinking like a scientist? Brad, we'll start with you.
Yeah, I would say one of the drawbacks of encouraging that constant open mindset is potentially entertaining bad ideas for too long. So entertaining them and trying them out, seeing like, hey, why might someone believe this? That's great. But at the same time, to me, a great case study of this is seeing science and how it changes so rapidly on the forefront with COVID. And there's several great examples there to where specifically ivermectin. Because initially that what came under emergency use authorization for good, we didn't know what was going on. Like, let's try everything. And out of that, once it was looked further at, like, yes, ivermectin can get rid of COVID in studies in culture cells, but the dose that you need to do that is going to be killing you. So in effect, it's not a good treatment for that. And that changed over time, where initially it was, let's try this, to where within a matter of weeks or even months later with how fast things were happening, if you didn't revisit that idea and we're stuck on the previous one of why aren't we trying ivermectin? Well, we did, and the results were not great and not promising. So keeping up with the actual nitty-gritty science until it's further refined is hard for people because it can change. Certain areas change so rapidly, like with COVID, with all the interest in funding there. Other areas take much slower and longer to do, which then offers a little more time to process what's going on.
Kristen, I'll have you go next.
I wrote on my shirt, my card, not really sure. Dot. But as I'm sitting here thinking, I think in my classes, a lot of them are making students look at the world in a different way environmentally. And a lot of students come into the class with one worldview and change their worldview in my class. And often that causes really uncomfortable Easters and Thanksgivings. And really, like, to the point where Uncle Joe will not talk to me anymore. And to some extent, that's great. And to some extent, that's why academia gets nailed sometimes, I think, because I want, and I'm not going to apologize, I want students to start to see the world in the big picture and all of that. But a lot of change fast when you're in a family unit. I think that's more socially maybe disruptive than sometimes I consider. I am able to stand against my family and say things, and sometimes it comes as a shock to students when they're like, hey, I learned this, and then they get slammed down in their families. They're like, I didn't even know that was coming. I didn't know Uncle Joe was going to yell at me. But sometimes that, and I don't know if that's a fault of science or a fault of society, but it's something that can come out of this, I feel like. Yeah.
Vincent?
I think there's two things that really come to mind when I think about the downsides of being like a scientist. The first one, the obvious low-hanging fruit here, is that it's difficult. You have to put in work. You have to think about possibilities and look at in terms of probabilities of being wrong. What could be influencing that? Things you can control, things you can't control, things you don't know that you don't know to account for. Like, if you really truly apply that critical lens to everything, you are thinking about a lot all of the time. So that is consuming. It's going to slow you down probably. Like, yes, the more you think like this, the better you get at it, the faster you do. But I mean, how many of us have had kind of that analysis paralysis whenever you're trying to do something simple, like what clothes do I want to buy or what dinner do I want to get today? Like, you are thinking about everything else and you get buried in what it is you're trying to do. So that's one downside that we see. And in the clinical world, we see that a lot because there is a certain level to which you're going to go in a clinical laboratory. Then there's the next step, which is like research laboratory. And you can't go that extra mile all the time, even if it is a valid question or something you need to know. It's not the time and the place. So you have to walk away from this question that you want to know the answer to, and that can be really, really difficult. So they're kind of, that's, I guess, the one big thing that really can kind of draw back, and we'll probably just leave it at that one. That's it.
I was going to say, that's why it's important to have trusted, reputable institutions so that you can farm out some of that thinking ideally. It may not be perfect, but hey, it's been vetted by this committee or this organization that's trustworthy. So I'm going to go with what they think, so I don't have to spend all that time and effort, because it can be cognitive overload. There's life to think about, jobs, everything else.
Yes.
You spoke to my librarian heart there with that. I mean, that's us in the library, is the idea of, you know, we've got the trusted sources that you need for your paper or for life in general. And, you know, that you don't have to think about it because we've already looked at it, or there are places out there that look at it already. So that's exactly what we do all the time. So. The final question we have, and then we did have one quick one on the chat there too, we'll come back to that, is how can schools, both K through 12 and colleges and universities, do a better job of thinking again? Kristen?
Have my card.
You have a card.
Yeah, I do. First one, just start earlier. start earlier, kindergarten, first grade, second grade. Kids come in with this knowledge, and I think start earlier means make sure that the teachers teaching kindergarten and nursery school, first grade, have an education in science and aren't afraid of science. Because I think that we don't do a good job educating our K-12 teachers in science. I think they're great at teaching, but I think that this is something that we don't value enough. And so if they had more experience with it, they would feel more comfortable doing it. The other thing I have written down in bold is be comfortable with the saying, I don't know, let's find out. That is the hallmark of a scientist, is we don't know everything. And you're not supposed to know everything, and nobody can be an expert in everything. And I think the lower you are in education, the more you think you have to be able to answer every question. That little kid, if he asks you what kind of frog that is and you don't know, you just tell him, let's go find. No student has ever shamed me for not knowing something. They're like, awesome, I might know something the teacher doesn't, let's go find out. We have the internet, we have libraries, we have also, you can just open your phone, listen to the sound, and it's going to tell me what that frog is. So there are so many ways to find out, but so I think just encouraging the enthusiasm for me for its biology. You can't keep kids away from nature. It's hard. You have to pull them away from it. So don't get them in there, keep them interested, and then keep them going from young. I can't tell you in my class how many people leave my class at the end and the exit survey is, I'm just mad I didn't know this stuff before, right? So keep them doing the science and let them know it earlier. That's really my spiel on this one.
Vincent, I'll go with you next.
I probably have not a good memory of how my K through 12, when I'm a famously terrible student. So if I were to pick something that might foster that more scientific mindset, my memory from schooling was a lot of emphasis on this is the information, memorize it, regurgitate it to me on an exam.
Absolutely.
And in my mind, that is the most, first, it's physically painful for me to do because I absolutely despise it, which is why I'm a bad student. But two, it's not the real emphasis of learning and thinking like a scientist. You want to be able to think critically and apply knowledge perhaps from well-vetted sources and use that to the current situation or circumstance. So the real value for education in my mind is learning how to find information and how to use that information to make a decision, draw a conclusion, etc. And when the emphasis is so much towards memorize the quadratic equation, which I never memorized, by the way.
He said proudly.
I did very well on my GREs despite not remembering my quadratic equation. So, but no, it's far more important is like, how can you use the quadratic equation, not tell me what it is. And so I really wish, and what I see a lot in my students is they are overly concerned with how much of this on a scale of 0 to 100%, how much of it have I memorized and can I give that to you on an exam? And what I actually want to know is, can you use it? And that's a really difficult shift. I'm sure most of you in college have already encountered that, like where you go from this is the correct answer according to the textbook to like, well, in this case, how is this information useful, relevant, or what's wrong with it in this case? So I think more critical thinking skills, in short, is a way we could foster a more scientific mindset.
Brad?
Yeah, I would say, an example that ties to what Kristin was talking about was for like K-12 educators, being comfortable with saying, I don't know. So I did outreach at K-12 schools in Oregon, getting them comfortable teaching these science kits that they had in a state repository. And we would basically go out there and demonstrate for a while, which is, hey, let's go through this kit and kind of get comfortable saying, I don't know. And then, okay, now the teachers, now you do it, and have them step in and do that, because it is unfortunately a little bit maybe heavier on the teach to the test, which is memorize this. When you have a question, I need to know that answer, instead of just being saying like, yeah, I'm not quite sure about that. And also that would help with that, removing the fear of failure or unknown, or saying you don't know. So quickly get over that, like fail fast if you're going to fail. Learn, adjust your ideas, your beliefs there, learn from it, move on, so that you can go on to the next step. And this is for, the educational level, at organization, institution levels, for example. And a lot of this is known through these psychological tips and tricks. It's just hard to implement. So for example, when you're on committees proposing doing ideas or things like this, there's like best practices, for example, of doing what's called a pre-mortem, which is getting the team together who arguably knows more about how they're going to implement this plan and the ins and outs of it, and saying, okay, let's say we deploy this idea or try this and it fails. Why did it fail? Beforehand, and approaching it with humility so that it's not a negative experience saying, oh, I think it failed because of this, but really a learning experience. Well, why might you say this? You know, famously, this is what went, or infamously went wrong with like the Challenger explosion, with an engineer saying these O-rings might not work, and then kind of blowing that off a little bit to where we need this launch to happen, so let's go ahead with it, instead of saying, well, why might this launch fail if we're planning on doing it here, and getting all of that input ahead of time, which you may have been able to anticipate something that was a critical failure in that case, versus other pilots or programs or things that committees and institutions and organizations are attempting to do could be refined and improved on the front end instead of a post-mortem, which is saying, oh, this thing didn't go so well, why did it go wrong? Because you can learn some of that on the front end. So trying to get over that fear of failure, the fear of ideas being wrong.
I'm gonna tell you again, also the science part, just try to make science something that is not portrayed. I mean, you just said it's hard. It is when you get to the master's level. It does not have to be when you're in grade school. It can just be interesting. It is the material that people are inherently interested in it. Once again, I always say when they take an intro bio class, I feel like this is the stuff you need to know to be a parent, to answer your 5-year-old's questions. And so if we can kind of get rid of the stigma that goes with science, I think people will be more likely to go into those fields. A lot of people still have the fear of, well, I can't do that, or I'm not really very good at that. And I don't think they know what that is, right? I don't think they've even given that a try. Usually, maybe it's chemistry, maybe it's physics. I think it's often math that they think that, and it's like a lot of this is not about math. Not that math is the devil. This is where you find out what math is for, in my mind. It's where we use the math. And to me, this is where the aha moment came. It's like, oh, X actually means how much gas is in there or whatever. It's actually, now I know why, not filling the bathtub, but something that I care about. And so I think that that's an important thing too.
That's those psychological tricks, I think, being important to where, like, I'm not good at math.
Right.
And switching it to what they call now a growth mindset, but like, I'm not good at math yet. What would I do right now if I want to get better at it?
I feel like scientific thinking is sort of growth mindset. I think they kind of go together.
Yeah, I can say from my own personal experience, I stopped taking science as a freshman in high school. And it was because I just didn't get it. And, and at that point in time and things like that. And then about 20 so years ago, and I know Kristin knows this, I became a fan of Alton Brown, the cooking guy.
Yeah.
Discovered the chemistry of cooking and went, why didn't I know, that's kind of stuff I would have loved to have done in high school.
Right.
But
I have a son who's a culinary arts guy. He also loves Alton Brown, but he's good at chemistry and he's good at being a chef. And all of it kind of goes together.
Yeah.
But he can't sit down and shut up. He was not great in school. He definitely is one that has to be moving and doing.
Yeah.
So that's the other thing about science, more moving and doing, less sitting and talking like we do in our class that I do with them.
So we did have something go through the chat here from Kirsten, but I think it might have somewhat be answered a little bit. She asked at what age should we start teaching students to unlearn and just let them discover?
Yeah.
And, and I think early
and often.
Yeah. So.
Yeah, but the teacher has to be ready for that. That's the problem. A teacher has to then say, it's okay to just go. But I feel like I know that I'm doing science because in high school I had a PhD, which was really nice. And he made us do independent study, which is basically design your own experiment. You have to do the whole thing. You have to come up with the equipment. You have to do it in biology. And 2 days out of 5 days a week, we were doing our own experimentation. We were running all over that school. We had rats. We had all the different things. I can't imagine what that professor or what the principal or the superintendent thought. But I learned pretty early how to set up experiments, how they failed miserably, how to try it again. And that made me have a lot of confidence to be a biologist, so.
Does anybody in the room here have any questions for our presenters, or are there any other questions from the on Zoom too? So
What's the distinct difference between learning and discovery, if there is even one? Because when we often talk about scientific thinking, we seem to separate knowledge and process of learning the knowledge. Rather than information, we forget that information experiment, like the process of the information, are more compatible together than they are distinctly separate. So just reflecting off my question, is there a difference there between learning and discovering, if that makes sense what I'm asking?
I'll start on that, I guess. I think in the way that I'm understanding it, the way I would distinguish it maybe between learning and discovery is that learning is fast tracking discovery. So if you start asking the question, what's this table made of now? You've got a few hundred years of people thinking about this and refining that idea that you can go figure out to fast track that, because it would take you your full lifetime at least to start digging into that question. And well, I mean, arguably, since the early philosophers, it's credited maybe firstly incorrectly or not to like some of the Greek philosophers asking those questions about what are these things made of. And so it'll fast track you instead of spending your entire life just trying to get to the idea of an atom. Well, okay, we already know atoms exist and what they're made of. So you can get it to your interest level and to the level that's meaningful to you.
anybody else want to add anything to that?
I like the idea of that fast track kind of thing, because again, there are things that we don't know still. And one thing that was done to some of my students a couple of years ago is there was a bounty put out. They said, if you can answer this question, you get an A on the next exam. And the question was, how does this test principle work? And the thing is, we have 100 years of using this test, and we know that it works, and that's it. We don't know how it works exactly. We have a couple guesses. We think it has to do with this or that, but like it went from being a very simple question to like, once you look into it more, oh my God, there's a lot of possible explanations for this. So we rely enough now on knowing that it works, and that's how we can go about our daily lives without exactly knowing why or how it works. So I still think there's that disconnect between like true discovery and then just learning about something. When we figure out how this works, it's going to be great. It's not going to change what we've been doing for 100 years, because through that process of testing and evaluating the results or the outcomes and controlling for all the variables, we know it will work, and we know it does this with an acceptable degree of reliability. So probably in the same area, but yeah, definitely distinct from one another.
I don't know if I'm pushing back, but in conservation in particular, there are so many basic things that are not yet known. So you say that we've had, you're in an older field than I am, vastly older, right? The natural history is old, but biology and ecology and all those things, not so old. So there are still basic facts and systems thinking and all these things that are, it's a conservation biology is a field, 1986. So I was alive, you were all, some of us were alive anyway. So it's relatively new, right? So there's still discovery to be done. I mean, the species of cricket that I did my research on, we were trying to get basic information from. So I think there is still, and I think this should be good news, not bad news, lots of discovery out there to be had. Many, every single person here could go out, dig in their backyard. I encourage you all to do it. Discover a new nematode, name it after yourself, and have a species named after you. I know everybody's naming the stars, but you can name the things in your soil. So there are millions of species that we don't know exist yet. So that's just, to me, it's learning, but it's discovering new things. And so there's still a lot of that basic stuff that still has to be done. We don't know within an order of magnitude how many species are on the planet. But the guess, I'm not kidding you, anybody remember? Between 3 and 100 million. That's our guess. I said, if you're in a math class, you're not gonna get that answer right. If you get the answer between 3 and 100 million, you missed that, you're right, that's not a fact. So we don't even have an order of magnitude of what's right. So I'm saying there's a lot of that out there. And that's the exciting part to me, is that discovery. But you are basing it all on, you know, when you're looking at a cricket, you know it's a cricket, and then you go find, you stand on everybody else's shoulders. All the information that's already there, which is the learning, and then you just take it the next step further, which would be the discovery. Is how I would look at it, maybe.
So the fields, I think, have like, different levels of development.
They do.
Like chemistry and physics, the low hanging fruit, the easy stuff to get's kind of been picked over mostly.
Yeah,
So I've heard it put like 100 years ago, you could be a third-rate scientist in physics, but publish first-rate research. You just do a little bit of algebra that we look at now, like that's trivial. They get this equation named after them and it's utilized,
Yeah.
which seems pretty insane. But today, I've also heard it put that like in physics, you could be a first-rate scientist doing essentially third-rate research because it's so hard. There's so little left. Not to say there's nothing left. There's still loads in chemistry, engineering, physics. But I also tend to agree with the idea that like chemistry and physics, these types of fields are more sciences of the 20th century. A lot of it's been developed where now sciences of the 21st century are these systems thinking type fields, biology, where we're just starting to come online to understand these a little bit better. And understanding is even hard to where we can't understand with
Right.
neural networks and things. We just know that they kind of work.
like
We don't
great,
really get it.
exactly.
Because it's complex systems. It's not, oh, if I change this, this has this direct effect on here. It's, well, no, there's 100 variables that affect that thing.
Exactly.
And that's a simple case actually in a lot of these. So those are where there's lower hanging fruit to where if you get into some of those complex systems thinking areas like biology and how all these
All the
equilibria
climate models and all of that.
interconnected. That's kind of the thinking of the future with lower hanging fruit, but it's also complex because it's a lot of really complex mathematical
A lot of-
models,
lots of
linear
statistics.
algebra,
Yeah, a lot of
statistics.
statistics.
these fields that are traditionally not loved.
Yeah. Did that answer your question? Okay. Okay. Do you have input into this? Do you have a thought?
I mean, just on the definition level, so you would say learning is understanding what's already been discovered and discovering is understanding what's yet to learn.
Yeah.
Yeah, that
Discovery is always
that
gonna
sounds like a good way to put it.
proceed
It's
If you
the next
discover
step.
Something new, like it's
Yeah.
gonna change potentially everything you've learned up to that point. You have to unlearn what it is you've accepted or learned previously.
Mhm.
And then if it is one of those big earth shattering, this completely redefines everything. An example in the clinical world is like, we did a lot of testing over the last 120 years based on physically observable characteristics, serology, for example. Because that's all we could do with our technology. That was the limit of our understanding. And as we move now into like mapping out the human genome and then molecular testing and figuring out the genetic sequences responsible for other things, we have to redefine how we approach testing and disease states, et cetera. And then now we've gotten to the point of genetic testing where it's not so much this gene sequence correlates to this disease state. It's 75% of the time, one of these 3 gene sequences will correlate to this potential disease state. And it just gets further and further and further. So the higher resolution you can approach something, the more and more you're gonna have to unlearn what you knew previously.
The
and
more
learn the new
complex it
stuff.
is.
So it's always a cascade of discovery, learning, discovery, so on and so forth.
You're all undergraduates, but the one thing that we learn, the higher you go in education, the more you know, you don't know. That's what happens when you're your age. Come learn all this stuff. I know all these things. And then you get your bachelor's and then you get your master's like, oh, wow, I didn't know anything. And then you go to your PhD and you're like, I knew even less, I mean, you get more specialized, but then you just find out how much there is still to know. It's not discouraging. It's just awareness. It's just a sort of, I'm not making this up, right? And we all agree.
No,
Yeah, it's just
well,
how.
I was just thinking, and I didn't bring my copy of the book with me, but the subtitle is Knowing What You Don't Know, or I can't think of what the subtitle is, but yeah, that basically plays on that, so.
So I've heard it put as a denominator problem. So like the maybe wrong stereotype of a insufferable undergrad coming out of their philosophy class thinking they understand everything because they think I know 900 things out of the 1,000 things that there are to know.
Right.
But you get the denominator wrong. There's not 1,000 things, there's 1,000,000 things,
Right.
and you know 900 of them.
Yeah. Right. Exactly, the denominator just gets bigger and bigger and bigger.
So if there's no other questions, then I am going to thank our panelists here today. There was a feedback form handed out here. Paula, I believe, will be putting the feedback form into, yeah, she did that. So I would have our attendees fill that in. Also, if our attendees need to put into the chat, if they're getting this, attending this for extra credit, we would appreciate you adding that to the chat as well, so we can record that. And other than that, thank you very much. This is a great discussion. I think we could talk about this for
Yes,
hours.
yeah,
So thank you very much.
thanks,
Thank
Amy.
you.
Yeah.